Good day. Welcome to the sixth lecture of metal forming. This lecture is actually the continuation of the last lecture. In the last lecture, we discussed about the metal mechanism of flat rolling process. So this is the continuation of the last lecture. So in the last lecture, we discussed the variation of velocity of metal flow. Here we can see when the material flow during the metal forming process, there will be a velocity increase for the metal flow. We can see the variation of the velocity increase. This is the through the rolling gap. When the material is flowing, there will be a velocity increase from V0 to Vf. And another velocity term which is used in the rolling process is Vr, that is the roll velocity. And that roll velocity is constant throughout the roll gap. And so this is the variation of the roll velocity Vr. And here we can see at a particular point, at this point, the roll velocity and the metal flow velocity is constant. Okay, both the values are same. That point is called a neutral point or no slip point. And to the left of this neutral point, the velocity of the roll is higher than that of the velocity of the metal flow. We can see from the distribution here. We can see this is the velocity profile of the roll, or the metal flow, and this is the velocity profile of the roller. Okay, and here we can see from the distribution the velocity of the metal flow is less than velocity of the rod. And to the right of this to the right of this neutral point, here we can see the metal flow velocity, that is this point, the metal flow velocity. This is the distribution of metal flow velocity, and which is higher than that of the velocity of the roller. This horizontal one is the velocity of the roller. So other than at any point between this gap, so this gap, we can see the x-axis is the starting point of the rolling gap, and y-y is the ending point of the roll gap. In between these x-axis and y-y sections, anywhere other than this neutral point, anywhere in the roll gap, we can see a relative motion between the metal and roll, because there is a difference in the velocity of the metal and roll. So this relative motion cause slip between the metal and roll, and also this is the reason for the friction between the roll and metal. So this neutral point, that is the point where relative velocity is equal to 0, or the velocity of roll and the velocity of the workpiece or the metal flow is constant or equal, and that point is called a neutral point or no slip point. To the left of this point, the roll moves faster than that of the workpiece, and to the right of this workpiece moves faster than that of the roll. So there is a relative velocity between the workpiece and the roll in the roll gap other than this neutral point. So this is already I explained. So here in this, this is the another figure showing this neutral point. This is the neutral point. We can see this is the neutral point. This one is the neutral point. And to the left of this neutral point, this is the rolling gap. In between this area is the roll gap in between the section x-x and y-y. This is the roll gap in between. And here already explained, in this area, the velocity of the workpiece is higher than that. Velocity of the roller is higher than that of the velocity of the workpiece. But in the exit area or exit zone, this is between the neutral point and the exit point y-y. So in these two area, the velocity of the workpiece is higher than that of the roller. At a neutral point, both the velocity of the workpiece and the roller is same. So this is already I explained what is zero slip point or neutral point. So this is the neutral point. So the amount of deformation possible in a single pass is limited by the friction between the roller. So we already seen there is a relative motion between the roller and the workpiece, and this relative motion causes slip between the roller and workpiece, and which is also a reason for the friction between the roller and workpiece. And the amount of friction between the roller and workpiece is the one of the important factor which affect the total reduction or total deformation during the single pass. The final product is either sheet or plate, with the former being less than 6 mm thick. We already discussed that in the first lectures. Lubrication is often useful to keep the workpiece from sticking to the rollers. So we commonly use lubrication. So because of the relative motion interface, the frictional force which opposes motion acts on the strip surface in the direction shown in the figure. So here we can see In this case, to the left of this is my neutral point or line passing through the neutral point. To the left of this neutral point, the velocity of roller is higher than that of the velocity of the workpiece. Okay, so here the direction of friction will be in this direction. The direction of friction will be in this direction because this roller opposes the motion of the movement of workpiece. So that motion, the opposing force is in the form of friction, and this is the direction of frictional force between the roller and the workpiece. And after this neutral point, the reverse relative motion direction is reversed, so that the frictional force direction also reversed, and this will be the direction of the friction force after the neutral point. So to the left and the right of this neutral point, actually the direction of friction is actually in opposite direction. So that is here because of the relative motion at the interface, the friction force with the opposite motion, the friction force is not in a single direction. We can see to the left and right we have friction forces with the opposite motion and act on a slip surface in the direction shown in figure. In rolling, friction force on the left of the neutral point must be greater than that of the friction force on the right. This is very important because we need to move the metal flow is actually in this direction. Metal flow direction is this direction. Okay, for the metal flow direction, the net force should be towards the right. Then only we got a we can pass workpiece through the rolling gap. The net force should be in this right way direction or towards the exit direction. This net force in the right direction only possible when the rolling force on the left of the neutral point must be greater than that of the pressure force on the right. Then only it is possible to move the workpiece in the forward direction. So this difference, so this friction force actually that is in the opposite direction, but its value is not constant, is not same. Both the friction force towards the neutral point in the left direction and in the right direction, both the values are not same. So the friction force in the left side in all rolling process, the friction force on the left of the neutral point must be greater than that of the friction force on the right. Then the resultant friction force will be in this direction. Okay, so that will help for the movement of the workpiece through the rolling gap. So the net friction force will be in the right direction, and which makes the rolling operation possible by pulling the strip into the rolling gap. So actually in the rolling process we are not supplying any type of external, commonly we are not supplying external push or pull for the movement of the workpiece through the rolling gap. Actually the friction between the roller and the strip or workpiece is actually helping for the forward motion of the workpiece, and for this forward motion of the workpiece, the net friction force should be in towards the right. Then only we can move the workpiece in the forward direction. So the net friction force and the surface velocity of the roll must be in the same direction in order to supply work to the system. That is also an important criteria for the forward motion of the workpiece through the rolling gap. Therefore, the neutral point should be located towards the exit in order to satisfy this requirement. This is also important. This neutral point is not at the center of this rolling gap. This is not at the center. Actually, this neutral point is located towards the exit of the rolling gap. Maybe here. That means actually here. Okay, this neutral point may be here. So towards the exit. If the neutral point is towards the exit, then only we got a net friction force to the right. This is an essential condition. Net friction force towards the right is an essential condition for the forward motion of the workpiece through the rolling gap. For that, this neutral point should be located towards the exit of the rolling gap. Then only we got a net friction force to the right of the rolling gap. So the forward slip in a strip rolling was defined as the relative difference between the roll surface speed and strip or workpiece exit speed. So forward slip in rolling is defined in terms of exit velocity of the strip Vf and surface velocity of the Vr. So here we have this is the workpiece exit velocity Vf and the surface velocity of the roller is Vr. Then we can say the forward slip is equal to Vf minus Vr divided by Vr. This is called a forward slip. So always this Vf is greater than, Vf is always greater than V0 and Vf always greater than Vr also. Okay, then there will be a net forward slip in this rolling process. Next, we are going to study about the force involved in the rolling process. So, up to this slide, we studied only the velocity distribution. Mainly, there are three velocity. The entry region of the workpiece, we have a velocity of v0, and in the exit region, we have a velocity of vf, exit velocity. And for the roller surface, also it has a velocity that is vr. And in between the rolling gap, there is a relation between this vf, v0, and vr. The essential condition for this rolling process is such that this vf should be greater than v0, and there will be a relative motion or relative velocity in the forward direction or towards the right. Then only the rolling process will be a possible one. Next, we will study about the forces involved in the rolling process. So actually, in the rolling process, we supply some amount of compressive force through this. See this, in this here we are supplying some compressive force in the vertical direction through the rollers, and this compressive force actually develop a radial force. See this. So when we apply some compressive force in the vertical direction, for example, we can give this is compressive force in the vertical direction, PV, that is the compressive force in the vertical direction. So when we supply this much amount of compressive force, it is resolved under a P component. A P component that is called a radial force is developed, and this is actually the force which is act from the roller to the workpiece. This is the radial force. So this radial force is the important force which is actually transmitted from the roller to the workpiece, radial force. And another force involved is the frictional force. So I already explained there is a friction between the workpiece and the roller, and this frictional force is actually towards the right, and this is the frictional force. F is the frictional force acting on the interface between this workpiece and the roller. So these are the main two forces involved in the rolling process. So between the entrance plane XX and neutral point, sheet moving slower than the roller surface, and the tangential friction force F acts in the direction to draw the metal into the roller. So the friction force always acting towards the right, such that this friction force actually draw the metal into the roller. So this is actually help for the forward motion of the material or workpiece through the rolling gap. On the exit side, so this is the exit side. This is the exit side, or after neutral point. This is the neutral point. After neutral point, we can say all the zone is exit zone of the neutral point. The sheet move faster than the roll surface, and the direction of the friction force is then reversed and oppose the delivery of the sheet from the rolls. So in this up to neutral point, we have friction force in this direction. In this direction, after neutral point, the relative motion direction is changed, so that this friction force direction also changed. Okay, so this is in this picture it is more clear. In this picture it is more clear. See this. Up to neutral point, this is the direction of the friction force, and after the neutral point, this will be the direction. But the net friction force will be towards the right. That is actually help for the forward motion of the workpiece through the rolling gap. So next we will discuss the roll pressure distribution. When we apply some amount of stress or pressure through the rollers into the workpiece, and what is the distribution of pressure in the rolling gap, and what is the distribution or actually how much amount of pressure is in the different areas of the rolling gap, we'll discuss. That is roll pressure distribution. And in this we already familiar with these terms. V0, that is the entry velocity of the workpiece. HB, that is the thickness of the workpiece at the entry, and VF, that is the velocity in the exit region, and HF is the thickness in the exit region. We know for a rolling process always VF will be greater than V0, and here this is the rolling gap. This is the rolling gap. In this rolling gap we have different angles there. The main important angle is the angle of bed, alpha. So this is actually the contact area starting at point A, and this is ending at point B, this contact area between the roller and workpiece, and this is the arc of contact between the roller and the workpiece, and the included angle between this arc of contact, this angle is called arc of bed, alpha. And here in this we can see the neutral point. Neutral point is located towards the exit region. So this is the neutral point, and to the left of this neutral point, the friction force acting in this direction, and to the right of the neutral point, the frictional force is acting in the opposite direction. This is the direction of frictional force. Okay, so to the left, velocity of the strip is less than velocity of the rod. To the right, velocity of the strip is greater than velocity of the rods. We already discussed that. Next, we are going to discuss about this roll pressure distribution. So these are the which are different terms which may involved in this for the calculation of the roll pressure distribution. For calculating or for the analysis of the roll pressure distribution, the main important analysis we use is slab analysis, and the slab analysis in plane strain rolling. So this is actually a simplified version of rolling. Here we consider one of the important assumptions we used here is plane strain rolling. What is plane strain rolling? In case of plane strain rolling, the strain in a particular direction will be zero. So we already discussed that for a rolling process. See this, in this rolling process, there is no change in the width of the workpiece during the rolling process. That means in this direction, the deformation or strain in this direction equal to zero. Only strain, we can see strain in this direction and strain in this direction only. Okay, so we can say the strain epsilon xx and epsilon yy is there, but epsilon z is equal to 0. So we can see this epsilon xx and epsilon yy only have one value, epsilon z is equal to 0, so that we can consider this rolling process as a plane strain problem. So that is why we consider this as a plane strain problem. This is called a slab analysis of the plane strain rolling. So here our study is limited to plane strain rolling. So here in this, by using slab analysis, we are going to calculate the pressure distribution in the rolling process, and using slab method of analysis for the plane strain stresses rolling can be analyzed. And slab method of analysis, we take an element from the workpiece and identify all the stresses acting on that element, including the friction force. So that is the main step of slab method of analysis. In the rolling process, we take a particular element from the workpiece during the rolling process and we analyze that workpiece. Okay, what are the different forces are acting on this on that element, and then we resolve that forces in the horizontal direction. Thereby, from that we got the stress distribution or pressure distribution in the rolling process. Note that only difference between the two elements in the direction of the friction force. So here I am taking two elements. So this is the slab analysis. In this slab analysis, this is two rollers, roller 1, in between the roller 1 and roller 2 a workpiece is moving. So here the initial thickness of the workpiece is h0. The after rolling process, its thickness is reduced to hf, and we take a workpiece with a uniform thickness. It has a thickness of 1 unit. Okay, 1 unit is the thickness of this workpiece. Sorry, width of the workpiece. We take the workpiece with the unit width. So that is also an important assumption in the in this analysis. So here I take a very small element. Very small element from the workpiece. So this red, yellow color one is the small element here. I used for analysis. This is the small element which is used for the analysis. And here, to the left of this element, the thickness is equal to S plus DH. S plus DH is the thickness of the element to the left of the, or in the, to the left of the element. And H is the thickness in the right side. Okay, so because of the rolling process, there will be a reduction in thickness. And for this element, the reduction in thickness is equal to DH. DH is the thickness reduction. Initially, it has a thickness of H plus DH. After, when it passed through the rolling gap, at the other side of the element, its thickness is reduced to H. And here in this element, this element is make an angle with this center of the roller, and that angle is phi. Phi is the angle. Phi is the angle that is made between the axis of the roller and the element. And d phi is the actually the angle, included angle in the element, d phi. This is the included angle. So that is about the very small element. And here this small element is in the slab analysis, we take the small element outside. So this is the small element. This is the small element, or this one is also the same small element. Okay, this one. This is the element which we are going to analyze. Okay, so this one is the small element, and also this one is also another picture of the small element. And this one is also another picture of the small element. Okay, so this is a different views of the element. So here in this picture, here there will be a distribution stress of the element, the horizontal stress. So the horizontal stress acting on this element here in this, to the right of the element, the horizontal stress or the stress in the x direction is equal to sigma x. But here its stress is equal to sigma x plus d sigma x. So there will be a stress variation because when it passing through the rolling gap at each point of the material, there will be a stress distribution. So the stress will vary, and that variation is d sigma x. That is the stress in the x direction or the horizontal direction. So there will be a stress in this direction during the rolling process. And the next one is the pressure acting in this workpiece. So here actually we applying a radial, applying a pressure in the vertical direction, and the one component of this pressure is acting in this radial direction. That is equal to P. P is the pressure in the radial direction. So this pressure in this radial direction also can be resolved into two components. It can be resolved into two components. Okay, so I will explain that components in the next diagram. And one more component is there, one more force or force component is there, that is the mu p, that is the frictional force. We know F is equal to mu when that is the equation of related to friction, where N is the normal acting in this acting and mu is the coefficient of friction. So F is the friction force. So here the normal acting is P. P is the normal pressure is acting. So we got the mu P, that is the mu P is the friction force acting along the surface of the workpiece material. So we will resolve in the slab method. It is nothing but we resolve all the forces in the horizontal direction, and using these resolved values, and we equate it to 0 because this is a balancing in the horizontal direction. All the forces are in equilibrium. So using that condition, we analyze we calculate the pressure distribution or stress distribution in the rolling gap. So this is the another diagram. So this element is actually in the entry region. That means from the starting point of the rolling gap to the neutral point, that is the entry zone. So this is the when the element is in the entry zone, this is the element. This is the picture or the distribution of different forces. And if this element is in the exit zone, this will be the different forces acting on the element. So this is the enlarged view of this same picture. We already discussed this one, sigma x plus d sigma x and sigma x. So corresponding to sigma x plus d sigma x, we have sigma x plus d sigma x into h plus dh into 1. That is the corresponding force. That is acting towards the right. So we take towards the right is positive and towards the left that is negative. Okay, that is the direction. So next force is sigma x. So that is acting towards the left. So we give negative. That is equal to sigma x into, and here the area is equal to h into 1. In this direction it is equal to 1. So the cross section area will be h into 1. So that is equal to h into 1. H into 1. So we got two forces which is actually in the horizontal direction. Next force is the P. We need to resolve this force P. Not P, that is the pressure. So we need to resolve this P in the horizontal direction. So here we can see this angle is phi. This angle is phi. The phi is nothing but it is the angle between the vertical and this element. This angle is the phi. So this will be also equal to the angle between the horizontal and this line or the surface of the workpiece. So this angle is phi. So here we can see when we resolve, we got this angle also will be phi, and here this will be 90 minus phi. This angle will be 90 minus phi. So from this we got the horizontal component. That means this horizontal component of P is equal to, this will be equal to P sin phi. This will be equal to P sin phi. And here also the horizontal component is equal to P sin phi. Okay. And so we got this horizontal component of pressure P sin phi. And we need to convert into force. Here we convert the stress into force by multiplying with the area. Similarly, this pressure P also should be converted into force. So how can we convert this into force? here in this we can see this arc length. So how much is the arc length? That means actually the area where this P is acting, this arc length into this area. Okay, so this is equal to 1, this is equal to 1, but we need to find out this arc length. So we know this angle is equal to d phi, already given here, d phi. And we know this radius is equal to r. Radius of this roller is equal to r. So we know that the arc length is equal to r d phi. R d phi is the arc length. So the total area of the strip where P is acting, that is equal to r d phi into 1, because the width of this strip is equal to 1. So we can convert this P into this P sin phi, that component of pressure acting horizontally, into force by multiplying with the r d phi into 1. R d phi into 1. Similarly, this also we can be convert P r into d phi into 1. So this will be a force. So these are the two forces corresponding to the pressure applied, or radial pressure, which is acting towards the left in the entry zone. In the entry zone of the element, both the pressure forces are acting towards the left of the workpiece. So towards the left we take as negative, so minus P sin phi. So here we have 2 P sin phi r d phi 1. So we can give 2 into P sin phi r d phi into 1. Okay, so that is the 2p r d phi sin phi. So we convert this term is okay. This one is okay. So we convert this P into horizontal component. Sigma x is completed. This P is also completed. Another one is the frictional force. So here we have mu P. So mu P also should convert into a horizontal component. For that, we know this angle is equal to phi. Similarly, this angle also will be equal to phi. Okay. So when we resolve this into a horizontal component and a vertical component, this will be the horizontal and vertical component. And the horizontal component will be mu P into cos phi. This will be mu P cos phi. And these are the two horizontal vertical component. This will be equal to mu P into cos phi. That is acting towards the right. So we give positive. So plus 2 into, and one more thing is that here the P term is pressure, not this force. So we need to convert this P into force by multiplying with the area. The area is equal to, again, r d phi into 1. R d phi into 1 is the area, similar to the previous case, into r d phi into 1. So we can give 2 into mu P cos phi r d phi into 1. So this element is in equilibrium. So sum of all the forces in the horizontal direction will be 0. So we can give this is equal to 0. So this is the equation we got, the same equation we got. And here in this, here we only analyze the exit zone, entry zone, entry zone. In the entry zone, we can see the mu P direction that is towards the right. See this, the mu P is towards the right. From the previous figures, we already discussed that in the entry zone, see this, in the entry zone, the mu P towards the right, but in the exit zone, the mu P towards the left. The relative motion of slip is different direction, so that here mu P in this towards the right, but here in the exit zone, the mu P is towards the left. The direction is reversed. The remaining P and sigma x plus Ax, this P, everything direction is same, but in the exit zone, the only difference is mu P direction is reversed. That means it is acting towards the left. That means here, instead of plus sign, we give negative sign. Okay, so same equation can be used for entry zone and exit zone, such that in case of entry zone, here we use plus sign. In the exit zone, here we use negative sign. Okay, that is the only difference. So this is the equation, corresponding equation. The summation of or equilibrium of all forces in the horizontal direction, that is equal to 0. Then here in this, we have different second order equations. That is, when we multiply these two terms, we got d sigma x into ds. And we can already this d sigma x and dh is very negligible quantity. When they multiply, again its value is reduced, so we can assume it as 0. So we neglect all the second order terms in this equation and we simplify the equation number 1, and so this is a simplified form of equation number 1. So here we use plus or minus. Plus is for the equation with the plus sign is for that is applicable in the entry zone. The equation with the negative sign is used in the exit zone. In rolling practice, the bit angle alpha is typically only few degrees. Maybe in practical case, probably the angle is less than 6 degree. So if the angle is, the bit angle is nothing but this angle. In case of rolling, this is the bit angle, angle of bite. Okay, this angle is probably very less in practical rolling cases. If it is less than 6 degree, we can assume this angle is very small value. So we can assume in this equation, this sine phi is equal to 5. Sine phi equal to 5 if this angle is very small. And we can assume this cos phi in this equation is equal to 1. So by this assumption, again we simplify the equation number 2 and we rewrite this equation like this. Equation number 3 is got by simplification. And this is only applicable where this angle of bite is very small. So because the angle involved are very small, P can be assumed as a principal stress. This P, so this angle alpha is very small. So this P can be assumed as a principal stress. Actually, it is acting at an angle with the vertical. But if this angle is very small, then we can consider as a principal stress. So we consider this P as a principal stress. Similarly, the horizontal force sigma x is also, that is a principal stress value, that is sigma x. So P minus sigma x is equal to 2 by root 3 into sigma f. So we studied this von Mises stress criteria in the last lectures, and this is the von Mises stress criteria: sigma 1 minus sigma 2 whole square plus sigma 2 minus sigma 3 whole square plus sigma 3 minus sigma 1 whole square is equal to 2 sigma 0 square. Our term was 2 sigma 0 square. That was the yield criteria or von Mises yield criteria. And this von Mises yield criteria can be, this equation can be converted in case of plane strain case. So how we can convert this equation can be converted like this: sigma 1 minus sigma 2 equal to 2 sigma 0 by root 3. Okay, so we reduce or simplify this equation, that is sigma 1 minus sigma 2 equal to 2 sigma 0 by root 3, or we can say that is equal to sigma f or sigma dash f, that is the flow stress of the material. Okay, so we simplify the von Mises criteria, and here in this rolling process we apply the simplified von Mises criteria is applied in this rolling process. So this is the here sigma 1 is equal to P. We already assume P is a principal stress value, and sigma is another principal stress value. Sigma 2, instead of sigma 2 we give sigma x. So sigma 1 minus sigma 2, instead of that we can give P minus sigma x. And here this 2 by root 3 sigma f, and which is equal to sigma dash f. So this is the application of the von Mises criteria in a plane strain rolling condition. So we got a equation number 4 by applying von Mises criteria. So this is the corresponding reference how we apply von Mises criteria in the plane strain case. This is not included in this slide is not included in our syllabus. This is just for a reference. So after that, here we replace this sigma x. Here in this equation, from this equation we got sigma x is equal to sigma dash f. That is the flow stress of the material. What is flow stress of the material? It is the amount of stress required for the flow of, or for the deformation of the material at a particular strain. That is the flow stress of the material. So we got sigma dash f minus P, or we can see 2 by root 3 sigma f minus P. So we replace sigma f in the previous equation. In this equation number 3, we have a sigma x value. We replace sigma x with the sigma dash f minus P. So that is this equation. This is the corresponding equation. We replace this sigma x with the P minus sigma dash f. And then again we simplify the equation number 5. We got equation number 6. Again, then we differentiate. Here we can differentiate this, and after differentiation we got equation number 7. Okay, so here in this equation we can see two here in the, before this plus sign we can see a differentiation. Here after plus sign we can see a differentiation. Here in this, the second term of differentiation, we got sigma dash f into h, sigma dash into h. So here in the most of the our engineering materials are strain hardened material. There is it's a limited plastic material, preferably plastic material. So in strain hardened material, what happened when we deform, strength will increase. Okay, during the cold working process, there will be a strain hardening. So when we deform the material, the strength will increase. That means when we do deformation, the sigma f will increase. Okay, when we do deformation, sorry, not sigma dash f, sigma f flow stress will increase with respect to the deformation. For example, this is my workpiece. I reduce the workpiece into this much of depth, and another case, the same workpiece is reduced to very lower value. This is the second case. Okay, in the first case, I reduced to S1. The first case I reduced to S1. The second case I reduced to S2. Okay, so when we compare the strength of the two components, the component with the thickness S1, the final product with the thickness S1 has a less strength than that of the S2 thickness workpiece or component. This is because of the strain hardening. So when the S value, the reduction is or the thickness, if the reduction of the thickness H is decreased, that means here instead of S2, instead of S1, we further decrease to S2. That is, the reduction thickness is decreased. And what happened? That means if we decrease the reduction thickness means the strain is increased. Okay, so when the strain is increased, correspondingly what happened? The flow stress of the material will increase, because when the strain is increased or deformation is increased, then there will be some strain hardening. The material strength is increased, so we need more amount of stress for the further deformation. Okay, that means when the reduction thickness decreased, okay, then correspondingly the flow stress will increase. Flow stress will be increased. That means here in this equation, if this quantity increased, H will decrease. H will decrease. In another case, if this quantity sigma dash f is decreased, H will increase. Both are in opposite direction. That means we can consider this sigma dash into H as a constant, because when one quantity increased, the H quantity sigma dash is increased, H is decreased. When sigma dash decreased, H is increased. Both are in opposite direction. Okay, it's response in the opposite direction. So we can, when we multiply these two quantities, we can say that is a constant. So when we differentiate a constant value, then that is equal to 0. That means we can consider this term as 0. Okay, this term as 0, or initially this term is 0. The differential of the constant, this is equal to 0. So here also again multiply, so the whole term will be 0. Okay, so the equation 7 can be rewritten by applying this condition. So this is the, after removing this term, we got this equation. Sorry, this equation. Okay, so let HF is the final thickness. That means after reduction, HF is the final thickness. HF. H is the initial thickness. H is the initial thickness. Then this is the relation between H and HF. By considering the arc between the HF and HF, this is the relation. And we can approximate this into H is equal to HF plus R phi square. We can assume like this or approximate like this. And here this can be applied. This H value can be applied in the equation 8. Here we can replace this H value. So by replacing, then after we do integration, after integration, we got the pressure, the radial pressure act from the roller to the workpiece. That is equal to C into sigma dash F H by R e raised to plus or minus mu h. And the plus or minus depend upon the where we consider the material. Is it in exit zone or entry zone? And here we have a term C, that is the constant of integration. So we need to remove this constant, and here the S value equal to this one. This is a simplified form. This one is a simplified form where H value equal to this one. Okay, and we need to find the constant value C. To find the constant value C, we apply the boundary condition. When the phi equal to alpha, that means phi equal to alpha means in this derivation, see this is the angle phi, this is the angle phi. When the phi equal to alpha means this will be the, this is alpha, that means it is the entry zone. Okay, when phi equal to 0 means phi equal to 0, this is phi. When phi equal to 0 means this is the point, this is the exit zone. Okay, so that is the two boundary conditions we applied here. When phi equal to alpha, then h is equal to h0, then phi is replaced with the alpha. So in the previous equation, we can replace h equal to h0 when phi equal to alpha. Then we can replace in this h value, the phi can be replaced with the alpha. So this is the first boundary condition. Second boundary condition, when phi equal to 0, then p is equal to sigma f dash. So that is the, at the exit, after exit point, there is no further deformation. That is the final deformation where it will be the closures of the material. Okay, so here in the exit entry zone, we got this C value, that is equal to R by HF e raised to mu HI. So we can write the equation. This equation we can rewrite. This equation can be rewrite by applying C value. So this is the equation in the entry zone for finding the pressure. Okay, so that means during the rolling process, this is the entry point, this is the exit point, and this one, at the center we have a neutral point. Not at the center, towards the exit we have a neutral point. So this region, this is the from the roll entrance to the gap to up to neutral point. So this area, to find the pressure distribution, we can use this equation. And another area is this one from the neutral point to exit region. This is from neutral point to exit region. In this region, we can apply this equation for finding the pressure during the metal flow. Okay, so here in this, from these two equations, we have different relation between the different values or different quantities, and we will discuss the what are the relation between the different parameters in this equation. First one, note that the pressure at any location in the roll gap is a function of h. It is a function of this roll P is a function of h at any point, and the angular position phi along the arc of contact. This is also a function of phi. So here we cannot see phi, but in the h equation we have an equation for h. In this equation of h we have a phi. So this p value, that means during the rolling process there will be some pressure. And this pressure is at any point in the roll gap is based on the h value and the phi value. Phi is nothing but it is the angle from center to corresponding point where we take the, or where we calculate the p value. So it's dependent upon the h and phi. So this is h and phi. Phi are the two factors which affect the pressure. The pressure increases with the increasing h value. So here we can see from this equation, here we can see this is a direct relationship between the pressure and h value. See this, that when h is increasing, then p also will increase. That means if we need higher reduction, for example, here we can see this is the first reduction, and same workpiece I am going to reduce into higher reduction. This is the higher reduction. Reduce to higher thickness. This is S0. This is S1. Okay, this is S. So initial workpiece S. In the first case, it is reduced to its thickness reduced to S1. In the second case, it is reduced to S0. Okay. So when we compare these two cases, in this S1 reduction, need more pressure. So with respect to this S value, the pressure requirement also will high. So that is pressure increase with the increase in the value of H. And again, the pressure increase with the increase in the strength of the material. Okay, for each material, the sigma f dash value is different. If you take aluminum material, we got 1 sigma f f dash value, because sigma f dash value is dependent upon, according to this equation, sigma f dash value so according to this equation, we can see the sigma f dash value is dependent upon sigma f. That is nothing but the amount of stress required for deformation, sigma f. So for each material, the sigma f value is different. Okay, so based on the sigma f value or sigma f dash value, this pressure will vary. Since in this equation we can see a relation between P and sigma f dash value. If sigma f dash value increased, P value also will increase. That means a material with a high yield strength need more amount of pressure for the deformation during the rolling process. Next one is pressure increase with the increase in the coefficient of friction. Here in this equation we can see this e raised to mu. Mu is the coefficient of friction. So when mu increases, correspondingly the pressure requirement also will increase. That is why we use different lubrications etc. for reducing the coefficient of friction value. Thereby we can reduce the amount of force or pressure required for rolling operation. Another important factor is R by H value, R by HF value. What is R? R is the radius of the roller. So it's an important question. We already discussed about this. We will use small diameter roll for rolling operation. Okay, if we have a choice of selecting a smaller roller and a higher diameter roller, which one you choose? Here, the small diameter roller is better one for rolling operation. We already discussed planetary roll etc. In planetary roll and for high roll etc. we use small diameter roller. What is the reason? Here, when we use small diameter roller, this R by HF value will decrease. If R is decreased, then R by HF value also will decrease. When R by HF value decreases, the pressure required for rolling operation also will decrease. See this in this equation we can see, not in this equation, here we have an H value, sorry, here we have C value, C. In this C value, in the previous here, see P equal to the constant C into sigma dash f h by e raised to mu h. So here the C value, what is C value? C value is nothing but R by HF. We have a term R by HF value. That means the pressure P is directly related to R by HF value. So if the radius of the roller increased, correspondingly the pressure required for rolling operation also will increase. That is why we are using small diameter roller for rolling operation. But one difficulty of using small diameter roller is that when we use smaller diameter roller, there is a chance for bending of the rollers. To avoid this type of bending, we use different types of backup rollers. For example, in case of planetary roll, we can see number of backup rollers for supporting small diameter roller. So this is the equation which give the answer for this question, where we use small diameter rod for rolling operation, which will reduce the friction or pressure requirement for rolling operation. And another one is the distribution of pressure based on the coefficient of friction. I already explained with respect to increase of coefficient of friction, the pressure also will increase. Here we can see the distribution. See this is the entry zone. That means this is the rolling gap starting here. This is the exit zone. Rolling is ending here. Okay, and here when we see the distribution of the pressure and this coefficient of friction, here we can see, here we use P by sigma dash f. This is called a dimensionless theoretical pressure distribution. Here instead of using P alone, we divide with the sigma dash f. This is actually for neglecting the effect of the material. Okay, so if we use P alone, then there will be a factor of material, that is the strain, hardening etc. may affect this distribution. So we use a dimensionless pressure distribution, that is P by sigma dash f. And here this is the variation of the pressure or the dimensionless pressure times with respect to mu value. If the mu value is equal to 0.4, we can see at the entry zone, the pressure requirement for the deformation is very small. It's almost very small. Okay, but it is increasing. It is increasing to very high value, like a hill. At the neutral point, we have very high pressure requirement. Okay, this much amount of pressure is required at the neutral point. Then from the neutral point to exit zone, the pressure requirement for the rolling is reduced. That means in the neutral point corresponding to this is the neutral point. This area for the deformation of material, in this area we need very huge amount of pressure. But here in this area and here in this area, at the entry and exit region or in the intermediate region, the pressure requirement is comparatively low. So this is called a friction hill with respect to the variation from the entry to exit. Based on the metal flow from entry to exit, there will be a increase in pressure. This is actually the pressure distribution with respect to this rolling gap. Okay, so there will be, we can see a friction hill, and but if this mu I is 0.3 by means of lubrications or any other method, we reduce the friction. We reduce the friction to 0.3. What happened? The maximum pressure is reduced. Maximum pressure required for the deformation is reduced. Again, when we reduce the mu value coefficient of friction to 0.2, again we can do the same material deformation or rolling process with a lower pressure. If we reduce to 0.1, this is the corresponding pressure requirement. So with respect to decreasing the friction between the roller and the material, we can reduce the frictional force requirement for rolling process. Okay, so that is the inference from this diagram. And one more important point we can notice here. Here, this is the neutral point. Maximum pressure actually developed in the neutral point where the slip is or the slip is equal to 0. So this is the neutral point corresponding to 0.4 mu. When we reduce mu value, the neutral point is shifted towards the exit. See this? This is the neutral point under different mu value. Okay. When mu equal to 0, then that means when there is no friction between the workpiece and roller, then the neutral point will be at the exit. This will be the location of the neutral point. And this is the location of neutral point at the lower values, and at a higher point for mu, this is the location of the neutral point. That means the neutral point is shifting from towards the exit when we reduce the coefficient of friction. Okay, we can reduce the coefficient of friction, but if there is no friction between the roller and the workpiece, then what happens? The neutral point will be at the exit point, or the maximum pressure will be developed only at the exit. Okay, so that is also important. There is a need of friction between the roller and the workpiece. We should not eliminate completely the friction between the roller and workpiece. There is a requirement. For the flow of workpiece through the roll gap, there is a requirement of friction. But this huge amount of friction between the roller and workpiece will affect, or which is the one reason for higher pressure requirement. This type of friction hill will develop under very high coefficient of friction. So that is the distribution here. In actual case, this is a theoretical distribution. In actual case, this is not such a peak, very pointing peak, but here it will be like a rounded one. It is not a pointed peak, it will be a rounded one. So determined experimentally, we have smooth curve with their peaks rounded off. Okay, this is called friction hill. That's an important point. Another one is the pressure distribution with respect to the reduction in thickness. How much it is reduced. In one case, I reduce to this much. In another case, I reduce same workpiece with this much thickness. In both cases, the thickness amount of reduction in thickness is different. So based on the amount of reduction in thickness, the pressure requirement also will vary. So this distribution is shown here. Here also we use the dimensionless value P by sigma dash F to avoid the influence of the material in this distribution. That is why we divide with the sigma dash F. If we divide with this sigma dash F, we can avoid the influence of the material on the pressure distribution. Here the only factor which affects the pressure distribution is the percentage of reduction. Here we can see in this red color, one is the distribution of pressure when the reduction is 50%. That means initially it has a thickness of the workpiece has a thickness of 100 mm. After reduction, after rolling, it is reduced to 50, 100 to 50. So this type of 50% of reduction, this type of friction hill again, this type of hill, the pressure hill we can see in this distribution. But when we reduce the reduction, thickness is reduced, that means we reduce the thickness to a higher value. Okay, very small, it is not a very small depth reduction. We reduce to an intermediate value. That means the 30% of reduction. So when we use 30% of reduction, this will not be the entry point, but the entry point shifted to this point. That is also important. So here when we consider a roller, in case of this red color reduction, in case of the red color reduction, this will be the entry point. But in case of a reduction, higher value of reduction, the higher value means higher thickness reduction, the entry point will be another one. Okay, entry point will be shifted towards the right. This is the entry point, but there is no change in the exit point. Exit point is same. So that is important. With respect to this percentage of reduction, the entry point for 10%, this is the entry point, and that means the rolling gap is starting here only. So with respect to percentage of reduction, we can see the distribution of pressure increasing from 1 to this value, and it is decreasing. At a maximum, it will reach a maximum peak value, then it is decreasing. And this is the another distribution. We can see at the neutral point we have maximum pressure. The neutral point is the point where the pressure is maximum, and the entry point and the exit point have minimum pressure. This is the distribution of pressure during the rolling process. And in this distribution, the area under this distribution, this is the area under this pressure distribution, that is actually the force required to overcome the frictional force between the roll and the sheet. So here in this previous case, in this case, when the frictional force is reduced, then the area under the coefficient of friction is reduced, then the area under the curve also can be reduced, then the amount of force or amount of energy required for this to overcome the friction can be reduced. So this is the area under the shaded region is the amount of force required to overcome the friction force. Area under the dashed line represents the force required to deform the metal in a plain homogeneous combustion. This is the amount of force required. To overcome the friction, we need to supply the force, and that is actually used for the deformation of the metal. So the total area, this much area is used for to overcome the friction, and the total area is used for the deformation. This the dashed line is actually the dashed line. Under the dashed line represents the force required for deformation, and the shaded area represents the amount of force required for overcome the friction force. So that is about the distribution of pressure during the rolling process. So up to this, I am finishing this lecture. So in this lecture, we studied about the distribution of pressure. We derive a formula for finding the distribution of pressure, and this formula is applicable for the entry zone, and this is applicable for the exit zone. And different factors which affect the distribution of pressure is also discussed in this lecture. Thank you.